The flux of flow plane of a vector Jr, vector field Jr across a surface S is defined by the scalar. So it's a scalar. The flux is a scalar. Like it's a number, I guess. Is equal to like the sum of the dot products of these things. So Jx multiplied by the sigma x. Is this sigma rho? I can't remember. But I think this is delta y delta z dy dz. Jx blah 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 blah. Okay, let's just move on. It can be visualized readily by considering a liquid of density rho of r flowing in a pipe of rectangular cross-section delta y delta z with velocity in this direction as shown in here. The vector field J of r, which is equal to this, is called a mass flux density. Density is mass over volume, so kg m minus 3. This is just speed, right? Velocity ms minus 2. So together, this is just kg m minus 2 s minus 2 kilograms per like area per second squared. kgm, no, ms minus 1 is velocity. So mass per area per second is the mass flux density. It has a dimension of mass, well, it told me anyways, mass per second per unit area. The flux of Jr, which is this thing, across the shaded surface is the mass flux of flow, mass flux of flow, mass per second. Flux, flux, flux 2 equal this stuff where R2 is a point on the surface. Right here. It gives the total mass crossing the surface per second along the direction of its normal. The flux of Jr across surface is the flux of this is the mass flux. Why does this have a 2? Flux 2 equal delta y delta z, which is the area here. Integrating across this area is summing up all these little pieces in this area. Jr dot Vx flux 1. I guess I didn't show it, but maybe this is the flux of 1 and this is the flux of 2. 1, 2, maybe. Ding is the mass flux on the back surface. The negative sign appearing because the normal is this way now. Surface element, the normal is facing this way. It chosen to be this way. It's so chosen that a flow into a closed volume is negative. Into a closed volume. Finally, we note that the total mass flux out of the volume, so net flux equal the flux going out plus the flux going in, uh, if that is the correct term, which is delta G of x, delta y, delta z. So this plus this supposedly gives this. Um, yeah, change in jx. Right, so if we add these up, we could factor out delta y, delta z, and the stuff that remains should just be the change in jx, so it makes sense. Okay, which is equal to delta tau, delta jx, delta x. So to make this fit cleanly, they added this thing, but if they added that thing, they need to cancel out the delta x. So they did all the shenanigans. Divergence. We can also consider a mass flux density. Is that mass flux density? We can also consider a mass flux density for a general velocity field, VR, equal I VXR. So this is just a normal vector field where like every point is a vector associated with it. J. We can also consider a mass flux density for a general velocity field. We can also consider a mass flux density for a general velocity field in the body of the liquid itself rather than in the rectangular pipe. A rectangular volume space in the fluid of following can still be imagined. The only difference is that in general there will be mass fluxes across the remaining four sides. So we're dealing with bing, 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 6 normals now. There will be mass flux across the remaining four sides, hence the total mass flux. The total mass flux out of the volume per unit volume in the case of infinitesimal small volumes is, oh my goodness. I guess this area is the volume now. Hence the total mass flux out of the volume per unit volume when it gets really, really small is this, where the integration symbol denotes integration over a closed surface. So closed surface. The divergence of a vector field at point R in space gives its total flux per unit volume. Oh my goodness. The divergence of a vector field at a point R in space gives its total flux or net outflow per unit volume coming out of the point R. That is passing through an infinitesimally small closed surface. Passing through an infinitesimally small closed surface surrounding the point R. House explode. Okay. So for each point in space, we imagine a really, really small, well, they say to imagine like a box, right? But I'm imagining a sphere. I don't think it matters though because it's all really, really, really small. I guess for the mathematics, I don't know. Since we're dealing with this formula is assuming we're working with a cube. But is it really though? I think it is. It is assuming. I don't know. I'll see when I read more. So each point is surrounded by a little cube, and the divergence is this divergence. The only difference and the total mass flux. So this is the total mass flux, where the integration symbol, the divergence of a vector field. Is the total mass flux the same as the divergence? Like, is that the same thing? Does it specify? We will assume it is until I Google it. I don't know. Let's try to make sense of this equation. Okay, the total mass flux out of the volume a rectangular space. Console imagine. Okay, so phi x plane. J dot. I forget the name of this sigma. I think it's sigma. J dot d sigma. That just gives flux. That's just normal flux. All right. So the flux around a closed surface we were dealing with, was this a surface here? That's just an area, which I guess is a surface, yeah. So this is also just normal surface stuff. Um, Closed surface, we want, hmm, hmm. Okay, this is just for one side. Dot D, so this is just for one side. So I think the sigma, the area, differential area vector, I think that has components of 0, 0, and I don't know, because that's what it is. The normal is just I. Am I? Does this make sense? So the dot here, whenever you have dot product, it tells you like the angle of, it compares the angle of two things, or like it has to do with the projection of something on something. So what are we doing? Mass flow. So playing, so we assume the water is spewing out like this. The dot product is just gonna project what? The mass times the velocity. I don't know. It's projecting that onto the direction of the normal. Either way, I think 0, 0. This could be wrong. This could be wrong. But in my head, since we're only dealing with one, since this I'll clarify. It will all be made clear in the future, surely, surely. Um, so instead of one thing here, where this is 0, 0, 1 thing, we're dealing with three things there. So when we add it up, this tau will be very present, spooky, which um, which gives us a reason to have this 1 over delta tau here. Maybe, maybe. Limit as delta approaches 0. Delta approaches 0. The change approaches 0. So right now the change is this. So the change is gonna approach 0. So it's just normal, like it's just normal definition of stuff. Okay, this could be rewritten as this. Well, it is rewritten, so you can actually work it out. J dot is jx. Oh my goodness. Okay, jx d this x plus, we don't need to write out all. We can just do it for one. D delta x is just dy dz. But I guess we're using delta x delta z. Oh, we're not actually differentiating. I mean integrating. Because we just turn this back into a limit. Maybe. 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 I don't know. Uh, Either way, this got turned into delta y delta z. I'm not sure how interchangeable dy dz and delta y delta z is. And how important that is, but we'll figure it out. So delta y delta z jx. Will we bring our buddy tau back in there? Our buddy tau. What's tau? Delta x delta y delta z. But it's 1 over delta tau, so it's 1 over delta x delta y delta z. This crosses off with this, so we're left with jx over delta x. And then repeat that for jy d sigma y jz d delta d sigma z. And you'll get this. And oh, would you look at that? It's the components of this aligns with this. The del. It seems that del and d and delta is used kind of interchangeably, maybe. So del del x, jx, del del y, jy del x, qed. I forget what this means, but we move. Let me check chat. There was no one here. There was 0 people there. Unless they're not talking, I don't know. I could even have chat set up wrong. Who knows? I'll drink water, regardless. Alright, Gauss's theorem. A finite closed surface S can be subdivided into many smaller closed surfaces. This is done by dividing the enclosed volume into many smaller volumes. The closed surfaces of the small volumes and then small. Oh my god. But it makes sense in my head. So you just chop it up into pieces, basically. The closed surface is the smaller, and then the small closed surface is in question. By applying 1.84, which is this that I have written over a lot, to each of these small closed surfaces, we find that okay, we're summing up all these stuff that we did here. So the sum of the limit of is this just like a direct copy paste? JR dot, but they have JR after. How much does that matter? Is my question. I'm not sure. JR dot D. So it's exactly copy pasted except these two switch spaces for some reason. Does that matter? Delta X, delta Y. I'm trying to think of integrations I've done in the past. Has the X ever went before it? I know you can move constants in and out, like no matter what. Can you move around to dx? I'm just going. We move. Okay. So we're integrating over surface, and we're summing up surfaces. Summing up is like basically another integral. So integral plus the surface integral will give us a triple integral. Oh my god, oh my goodness. Uh, um, so dot .jr comes here. Delta, well this, what? Alright, the integral of our closed surface of a very closed surface is equal to the sum of the smaller closed surfaces. Sum of equal small closed surfaces equal the volume equal the volume. Like this is just volume. And hmm, let's just read this. Maybe it makes more sense. This integral relation is known as Gauss's theorem. It states that the net outflow across a closed surface S is equal to the total divergence in the volume omega inside S. As a result, we may say that the enclosed divergence causes the outflow. That is, the enclosed divergence is a source of the outflow. This sounds like magic. You're just making stuff up. Um, the net outflow across the closed surface. So stuff is coming out, stuff is coming in, maybe, but stuff is coming out. The net outflow is equal to the total divergence inside the volume S, inside S. As a result, so the net is equal to the sum of all the divergences inside. Um, As a result, we must say that the enclosed divergence, we can say it, but he has it in quotation, so maybe it doesn't cause it. So it's just like loosely. That is, the enclosed divergence is a source of the outflow, in quotations again. The enclosed divergence is a source of the outflow. The most familiar example of the application of Gauss theorem is in electrostatics, where the electric field line is known to be related to charge density from this, where bling, blah 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 blah. As a result, blah blah. This process of electrostatics state that the total flux of the electric field intensity coming out across a closed surface is proportional to the total charge inside this surface. For this reason, we consider Q, or more specifically, is this charge density. So rho just means density. It can mean any kind of density, depending on the context. For this reason, we consider Q, or more specifically, charge density, to be the scalar source of ER. Scalar source of ER. In this language, a solenoidal, which is divergence-free, vector field is said to exist without the help. Oh my god. In this language, a divergence-free vector field is said to exist without the help of a scalar source, because by definition, it's a divergence-free field. It's divergence-free. Its source density is not a scalar field, but a vector field. It's not a scalar field, as we shall see in the next section. Ooh, spoilers, ooh. Okay. Let me reread this real quick. Most familiar example, electrostatic, where the electric field plane is known to be related to the charge density as follows. So, a number, just like a normal number, multiplied by the charge density. No, not even the sum of the charge density, just the charge density. What? Electric field intensity. Left on notice the result. Total flux of electric coming out of a closed surface, which is this. It's proportional to total charge enclosed by the surface. Charge enclosed. Is this volume there? Volume multiplied by charge density, which is charge over volume, I would assume. Charge over, I forget the units for this. Coulomb's law. What does Coulomb's law say? Is that the force equal Q1, Q2 over R squared K epsilon naught? 1 over epsilon naught K? Well, let us move on. Um, show that the electrostatic field density ER of a point charge Q at the origin has an inverse codependence R, which means that the angular components of E must vanish because with the point charge at the origin, right, we have the origin here, the point charge is here. Because with the point charge at the origin, there is no preferred angular direction. The angular components of E should are denoted at of a point charge. Because hence ER equal. I get what they're trying to say. It just sounds a little complicated. They're just saying that the point charge um, shoots out all its stuff radially, and it has no preference. Like it doesn't really bend and stuff, and it doesn't have like more arrows on top and more arrows below. But like the bending thing is really important, I guess. Not I guess. The bending thing, the fact that it doesn't bend means that the electric field at any point would just be the radial direction. Hence, the electric field at R equal the magnitude, and the direction is just radial. Consider next a spherical surface of radius R surrounding Q. Right. On this surface, oh my god, spherical coordinates. I don't. Oh, spherical coordinates is an entire like study session in and of itself. So I'll just take its word for it. Like I've done it before, but I forget all the specifics. Um, spherical surface of R surrounding Q. On the surface, the um the differential area element would be equal to this, hmm, where this is this. I don't know why they made it like this for. Um, Omega being called a solid angle, I guess. Like, yeah, I forgot about that. Gauss's law then gives Q over U, blah blah blah. Dot. So all this hmm, E dot is. So again, they put the differential area element before the E again. I know where. Oh, it was in front. Anyways. Hmm. Okay. So dot product. Well, both of them in the same direction, so there'll be no like there'll be no like fraction or anything. It'll just be these two multiplied. Uh, hmm. I can't see what is in the way. Uh, I am not that neurodivergent. Draw. I am lost. Cursor? No, you. Line. Line. Since it's all down spheres, this. Okay, what? So they pulled out all the constants. Is this a constant though? Is that a constant? Oh, we're integrating over the phi d theta. What is d theta? Okay, I think d theta is like d phi is up and the theta is like across or something. And they're saying that um, from here to here, or here to here, the electric field is the same because that's just how it is. It makes sense in my head because like the distance from here to here is the same, and that's why R is treated as constant too because no matter if you change the angles, which we are doing because the phi, the cos theta, R will be the same. So we pull out the constants and integrate the solid angle. They did that over here. You get 4 pi, blah blah blah. Hence, the electric field is in the radial direction. The charge over these stuff. And R squared at the bottom shows that it has an inverse square dependence. Oh my goodness. Okay, so let me try to, even though I'll do this in another time, let me try to make sense of this. Alright, so we're double integrating one of, okay, 0 to 2 pi. That's just a circle. That's just a circle. 1 to minus 1. Why is it 1 to minus 1? I know the upper and lower bounds of cos theta is 1 minus 1. 1 minus 1. 0. Hmm. Integrals 1 minus 1. But who said we move, we move? Is anyone there in chat? Nobody is here. Wow. Unless I have set this up wrong, which is very possible. Okay, continuity equation. If a fluid is in a region of space where there is neither a source nor a sink, the total mass, they didn't define sink, I'm just going to say that. I guess they assume we know what a sink is. I think I know what a sink is. It's just the opposite of a sausage. Like it steals the flow, like a black hole or something. If a fluid is in a region of space where there is neither a source nor a sink, the total mass flow out of a volume expresses itself as a rate. A fluid is in a region of space. There's no source, there's no sink. The total mass flow out of a volume expresses itself as a rate of decrease of the total mass in the volume. So we have some fluids in there. If it have some um, if it have some outflow, it is gone forever. Like this keeps decreasing. So there's a rate of decrease of the total mass in the volume. So the overall density should get lower as well, obviously. Mass conservation requires an exact balance between these effects. That is the total mass flow out. Yeah, it makes sense. Okay. It's exactly what I just said. Um, exact balance means that one thing should be the negative of the other thing. So that's why there's a negative here. so that when you add them up, it'll be 0, so they cancel out. Ah. Mass conservation requires examples of these fires. Rate of decrease. When you differentiate by time, it's basically that's what rate is all about, I guess. Um, uh, Mass flow out. And mass flow is just J of R, which is the density times velocity stuff we did earlier, times the area. Okay. Why is this d tau here? I guess it's just to be like over the entire volume. Um, okay. So this happens. So this turns into this after applying Gauss's theorem. The first and last expressions. I assume this is the first, and this is the last. Show that mass conservation requires that the equation requires that playing equals 0. Okay. So if we just pretend, I don't think we could do this, but if we just cancel out the integrals here and here, this is copy pasted into here, and this is copy pasted here. So that is in a world where we can just cancel out the integrations. But I assume we can't. I assume I'm correct too. Maybe I'm wrong. So let me try to make sense of that. Okay. But yeah, this equation makes sense. Granted, these two are equal. So let me try to see how these two are equal. So let me finish reading this. After applying Gauss theorem, we got this, which shows that when you add up these two equals this, it must be satisfied everywhere in the volume. This is called the continuity equation for a conserved current. Conserved current. I guess conserved comes from you're conserving the mass, like nothing is happening to the mass, because the mass is just leaving. I don't know. I just need to read some more because it just says the current is this mass flux density. Am I saying that correct? Mass flux. Let me scroll up. What is J of R? J of R is mass flux density, yeah. Conserved current, JR. Okay. Gauss's theorem. Where's Gauss's theorem? Where are you, son? Where are you? It says you can change this into a volume integral. You can interchange between these two. I assume you can interchange it. It states that the net outflow is equal to, so it should be interchangeable. I guess let me screenshot this and put it in like my notes place. I don't know. I might as well get the entire thing. Fire alpaca, my beloved. Let me see if I remember how to use this. Why is Okay. Am I in white? Yeah. Ah, but you, you, is it really that small? Um, ah, I forget how to do this. Okay, I'll just write it. I'll just, do I just use my memory? No, I'll write it down. Closed surface, JR, d sigma. Closed surface, d differential, like thing, JR equal, um, volume d tau, divergence of JR. Volume d tau. Is this the correct way? Tau? Looks like a J, probably not. Maybe it's this way. Oh my god. dt. Divergence dot JR. Okay. Okay. Um, where was I? Alright, yeah. What was I on about? Total mass out of volume. Rate of decrease of the total mass and the volume. Okay, so this is allegedly the total mass. They're summing up for every instance in the volume, every like point, every little piece section. They're summing up the density, which is, well, mass over volume, kg over m cubed, and the tau is just m cubed. So m cubed cancel out with n minus 3 to give me kilograms. And del LT is just kilograms per second. So this makes sense. So if you want to find a rate, if you want to like formalize, is that a word? And even if you want to termalize, like make into a term, if you want to express a rate of decrease of something, you do del T, because that is rate, maybe negative, if you defined decrease to be like the opposite of something else, which would be increase. Um, Rate of decrease of a total mass. And then you just shove something, that means you just shove in a term that is the thing that is decreasing. So this is one way of writing the total mass of the region of space. Okay, so this makes sense. And we equating it to the total mass flow out of volume, which is, yeah, which is, did we change this to this from like earlier? Let me check. Let me commit it to memory first. PRVR.d line, blah, 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 line. dot PV. Divergence of PV. Yeah, technically, yeah. So we already proved this earlier. So I don't need to reprove it to myself. So we just said this is equal to this. Okay. Hmm. 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 Now all I need to do is make sense of why. Wow, I'm really running out of colors. I need to make sense of why it works as if these two are cancelled out. Can you do that? Well, you could just be like, oh, I'm dividing. Well, not dividing, I'm differentiating over the volume now. Is that a thing you can do? Because I know differentiating is the opposite of integrating, but can. Because integrating has like limits, right? So if I'm integrating this curve, I'm integrating from here to here. But differentiating. Hmm. No, that's I'm mixing up definite integrals and indefinite integrals. Definite integrals gives you an actual value. Um, the definite integ and if you did that to like the gradient, well, if you did that to the differential, you'd get a gradient, I think. Maybe I'm talking nonsense, but like I feel like Newton was talking nonsense, but like he proved to himself that yes, this nonsense makes sense, and this nonsense makes sense too, tragically. Um, okay, so hmm. I guess it makes sense. Like if we treat this as an indefinite integral, which it kind of is it? We haven't really plugged in any values. We could just be like with differentiating. Uh, I will accept that reasoning. Maybe I'll take a break right now. I don't know. Hmm. Wow, I just yapped for an hour straight. Good job. Good job, my friend. Good boy. What did you just call me? I'm talking to myself again. Oh, oh my god. Oh, oh. Oh, let me try while I'm in my break in quotation, because I'm just blah blah blah. I'm trying to figure this out. Um, I already did some weird stuff, like I offset it. Okay. Oh, it's right here. I just need to scroll up. Okay. How do I select it though? You, you, you. Yeah, you. How do I enlarge you? Um, select, transform, boom. Wow, that is wow. Ah, maybe let's keep you like this, buddy. Uh, maybe we can just zoom in, transform. Deselect. Oh yeah, I can just zoom in. How does that look on the stream? It looks good. I just need to um I just need to make my pen really really small now. Yeah, that's good. Um hmm, hmm, hmm. Place to write stuff. Surely that's legible. Is that the word? I don't know. I don't know. I don't know. Okay, that is enough of a break. How are you doing, my boy? Really, really good. All right, that's enough chat engagement. We we move forward. Okay. Okay, this one might be like really tough. Is like this is just theory, like integral and differential theory, I assume. Gauss's theorem, 1.85, can be applied to the vector field VR to give. What is Gauss's theorem? I think that's what I wrote. Gauss's theorem. It changes surface to volume. The end. That is it. It changes surface to volume. Can be applied to a vector field VR to give. Alright, we started off with this. We change it to a volume, but we deal with the I component. Well, one component so far. Del del xi, blah blah blah. Alright, I follow so far. Can we apply the vector field to give this? Since this is true for does this have no J and K components? Is that what this is saying? VR equal EI this. I think that's what that's saying. Unless it's some crazy thing like a dyad. I don't even know what a dyad is. But I've heard scary stories. Since this is true, yeah, otherwise this would be like I was gonna say we would have like two summations here, with like I goes from 1 to 3, but they didn't really specify that this is the full thing. So maybe that was unnecessary anyways. If this had J and K. Since this is true, let me shut up. Since this is true for any I, it follows that when we sum it up, EI blah blah, the normal thing equals EI balloon. Did anything change from here? U, U, U. We just okay. It follows that this equal this, I agree. Equal this, I agree. Do I agree? I agree. I wasn't there a dot here? Wasn't there a dot here earlier? Was there not a dot there? Okay, omega d tau dot jr. well, dot whatever, d tau dot j. Where is the dot? Where did you go, my friend? Oh boy. Since this is true for any I, well, this, this, this is true for any I. Bling, bong. Oh, this is closed and this is not closed? Is that the difference? What is a closed volume and what is not a closed volume? A closed volume. Aren't volumes closed by definition? Like, what is an open volume? Like, even if you draw a cube and you put a hole in it, the hole ends at some point, and like the area around the volume around it will just be the volume. I'll have to ask my good friend being the AI Copilot. I'll have to ask them if there's a difference between closed volume and normal volume. Maybe I should write that down over here. I should write down my questions. Closed volume versus norm. Uh, this is just regular volume. Okay. Blah. Why is the dot gone? Okay. Some of this, I guess they're being like, oh, this was just a third integral. Woohoo! Yippee! This turns into this. This. But then not. Oh my god. This result generalized. Let's ignore the dot for now. This result generalizes Gauss's theorem to the upright identity. This. So we started off with boom phi. We ended off with boom phi. This result generalizes Gauss's theorem to the upright identity. For operations on any field in space. That's a big claim. It gives rise to other integral theorems such as oh boy. Cross theta boom boom boom. I want you in my room. They're just replacing this with this and calling it a day. Replacing this with this, they're calling it a day. And this is just two things. This turns into this. Ah. D tau. Operator. This goes into this. This goes into this. The x of this pairs over the x of this. This seems more complicated than it appears. Well, this seems less complicated than it. I feel like it actually is. Like let me get into this. So the dot product is just saying that the x of this, which is del del x. We just draw a line here, so we know we try to equate to these two things. Del x. Oh, this acts on this as well, like this entire bracket. So what's the x component of this? Let me just go off of vibes, and hopefully it's correct. U del x v minus v del x u del x u, and then del y. Wait, why am I doing equal sign? We have to multiply these things. Do we? Yeah, we do. So we have to multiply these things. So del x of this. Oh my god. I haven't. Is this a triple? Oh baby, a triple. No. This is just. Is it? I haven't done a differentiation in a while, even though I'm reading this complicated book. So there's kind of like. It's kind of like a clash in there. This is why we clash. So we are differentiating a product, which is, we leave one thing alone. So let's leave the u alone and then differentiate this, which will just be del 2 del x v, and we just add that to the opposite. We leave this alone, del x v, and then we act on this del u del x. That is very messy. Okay. And now we have to do the same thing for this, because all that is just this one term. We need to also do it to this guy. So del. Right, let's just del v del. Let me go back to purple since it's technically a lighter purple pink. Yeah, it's technically the same bracket. Well, those two different terms, expressions, is the same like bracket. The x component of this bracket. Del v del x del u del x. Remember, this is negative, so this should cancel out with this, I assume. Plus, which is a plus, but this minus still acts on that, so it's also a minus. Del del del. We already did del v, so we need to differentiate this again. It's minus v del 2 del x squared. That is acting on u. So these two things cancel out, and we're left with u. We're left with u del 2 del x v minus v del 2 del x squared u, which is precisely this. And if we add up this is just the x. If we add up the y and the z, I trust that it'll just end up looking like this in the long run. So yeah, I can work with that. I approve. The last identity is called Green's theorem. Okay. So Green's theorem is, oh my god, what does this even mean? Green's theorem is the integral over a closed surface of of are these scalar vectors? The scalar fields? Are these even fields? They have to be fields because we're integrating x, y, and z. So they have to have x, y, and z components. Surely. What even is a field? Like, is a line? Do functions count as fields? That's a word question. Um, we move. The application of these formulas is certain list of examples. Show that this equal this. I feel like I need another break. Like this section specifically is more brain power than normal. I guess I'll take another break. Is anybody in the chat? Let me engage with the chat. Yo, chat. Um, good, good, um, good, just good. Let me drink some water. I wonder if anyone like showed up and left. I don't know. I don't know a thing. I don't know a thing. I know a bunch of things actually. Um, okay, break over. We move. Um, so you can use these theorems to like simplify weird stuff. Show that this equal this. This is equivalent to showing that ah, hmm, bling, bling. Why is there a dot here? This is equivalent to showing that the divergence of this equal this. Divergence. Yeah, yeah, I agree because this is this, but this is missing the divergence. Well, the gradient function. Is that what I call the gradient function? Um, wait, but hmm, this is equivalent to show. Maybe I need a permanent break, but I trust them. I trust them. A result that can be demonstrated readily in rectangular coordinates. Yeah. Calculate this over a closed surface. We have a closed surface. My default closed surface is like a hemisphere. Because if you want like to do basic stuff, you can just use a flat surface. But if you are into like, if you ever need to go like crazy mode, you can deal with the curved surface. Um, Calculate this over closed surface. So we just change this into this because we could do that. Can you really do that? Like, is that actually a thing you can do? I mean, it makes sense, but Won't you lose like some meaning in the conversion? But I guess closed surface and volume is kind of like they're kind of related. Like you can visualize it easily. Now why is it 0? Calculate this over 0. Okay. Um, this is in the way, sadly. Goodbye, my good hemisphere friend. Is okay, draw. So cross multiply. JK. Hopefully I still know how to do this. Um, del is just del LX, del Y, del C, R is X, Y, C. This is this minus this. dz dy, d minus dy dz. What? Why is this 0? Does it have to do with this? Or maybe it's like they cancel out because like how these two loops, if this is going this way and this is going this way, this section cancels out. Calculate this O equals to this. Equal this. Thing cross R. Cross R. X, Y, Z. Right? R is X, Y, Z, right? Right? dx, dy, dz. dz, dy minus dy, dz. Minus dz, dx. Oh my god. Show that this is 3 times the volume. Show that for a closed surface R dot R. So the area element, and R, the dot product of those two is 3 times the volume V enclosed by the closed surface S. So this, we turn this into this. What does this R stand for? Enclosed by the surface S. Why is this an R? Region? Maybe. So we ignore this right now. This turns into 3. Del X, del X, del Y, del Y. Del C, this del C. It's just 3. So 3, and this is just volume. Okay. I see the vision. I see the vision. Volume. DZ, okay. I'm still hung up over this. Let me just zoom in into just dz dy minus dy dz. And let me just, why not multiply by, let me pretend this is dx dy dz. So dx dy dz, dx dy dz. dy and this cancel out, dz and this cancel out, dy, dx, dz, dx could factor out to give dz minus dz equals dx multiplied by 0, which means 0. So we get 3 zeros. I didn't think this would actually lead anywhere, but it kind of did lead somewhere. But I based this off of like what I thought was nonsense, which is changing this to dx, dy, dz. It kind of worked out. I don't know. It's good enough. It's good enough for me. Among Us reference. Ah! I thought I already did this. I thought I already did. Oh my. And there's even more. There's even more. There's even more. Um, maybe I'll stop for today. Maybe I'll stop for today. But then again, I think I'm on a roll. Like, it is 1:50 a.m. Maybe I should stop. Thank you to my 0 viewers. Thank you to myself for talking so much. See you. Make sure to subscribe. And thank you for all the bits. Goodbye.